Hello everyone, and thanks for watching Edupedia World videos. So in this session of states of matter, we'll talk about Dalton's law of partial pressure. So first we'll understand the meaning of the term partial pressure, and then we'll look at the Dalton's law about partial pressures. Okay, we'll try and understand the law's statement, and then we'll go to a numerical approach of Dalton's law. So first let's understand the term partial pressure. Why and when do we use this term? So let's say we have a container having an ideal gas. If that ideal gas, if of a particular kind, say it is nitrogen, okay, so in that case, what is the pressure inside the container? Okay, so we just say what is the pressure inside the container. We don't say something like what is the partial pressure inside the container. But if instead of just having one gas, what if we have more than one gas? Say I also have oxygen over here. Okay, so I also have oxygen gas. Now when I ask you what is the pressure inside the containers, what does that term mean? Am I talking about pressure due to nitrogen molecules, pressure due to oxygen molecules, or is it that I am talking about the total pressure inside the container? We can't say, right? So hence, to differentiate that, we use the term partial pressure, as in I'm not talking about the pressure in its entirety, I'm just talking about a part of the pressure. Let's say I'm just talking about the pressure which is exerted because of the presence of oxygen molecules. Okay, so hence partial pressure is nothing but the pressure exerted by an individual gas inside a given container. Okay, that is, if we have a mixture of different gases present in the same container, alright, then the pressure exerted by one single gas, say oxygen, will be the partial pressure of oxygen. Pressure exerted by another single gas, say nitrogen, will be the partial pressure of nitrogen inside that container. So it is the pressure of an individual gas in a given mixture of gases. It is represented by small p. Actually there is no standard representation of partial pressure. Okay, there is no standard symbol, but usually what we will do is, okay, what we will use over here is, to talk about total pressure we'll use capital P or PT. Okay, that is the total pressure inside the container, and to talk about partial pressure of, say, gas A, we will use small p with subscript, say, A. Okay, or say partial pressure of nitrogen, so small p with subscript N2. Alright, so P is, how do I calculate the value of P? Okay, so now that is what we have to understand. So partial pressure is calculated as if the whole container was occupied by that single individual gas only. While calculating partial pressure, I will ignore the other gases present inside my container. Let's say this is my container having three different kinds of gases, gas 1, 2 and 3. Okay, let's say the amount of gas 1 is N1 mole, the amount of gas 2 is N2 mole, and the amount of gas inside is N3 mole. Okay. So when I have to calculate partial pressure of gas 1, what I will do is, I will completely ignore gas 2 and gas 3. I will assume that this complete container of volume V is occupied by gas 1 only. Okay, and then I will calculate the volume, the pressure exerted by that gas inside this container. How do I calculate that? Simply by using our equation of state, PV is equal to nRT. So pressure P is equal to nRT by V, where pressure P is the partial pressure of gas 1, so let's represent it with P1. N is number of moles of gas 1, so let's represent it with N1. R is universal gas constant. T is temperature of that container, so temperature of the container and inside the container is same irrespective of which gas you are talking about, right? It's not like the molecules of gas 2 are going to experience a different temperature than molecules of gas 1. They will all have same temperature values. And volume V is the volume of your container. Okay, so using this formula I can calculate partial pressure due to gas 1, okay, or pressure exerted only because of gas 1. Similarly, I can calculate partial pressure of gas 2 as P2 equals to N2 RT by V. Okay, so you will notice here that R is obviously same in both the equations. Temperature and volume also have same value in both the equations 1 and equation 2. And lastly, partial pressure of gas 3 can also be calculated as P3 equals to N3 RT by V. Okay, so here again RT and V have the same values, only difference is between the values of N1, N2 and N3. Hence, partial pressure, the change in the value of partial pressures, that is the change in the value of individual pressures of each gas, is a direct result of the change in the value of number of moles of that gas inside the container. Okay, that means the partial pressure or the pressure exerted by gas 1 and gas 2 are different because amount of gas 1 and gas 2 inside the container are different, because rest all the variables are same for all the three gases. Okay, so you must understand this concept of partial pressure, and you must also understand the mathematical formulation and calculation of partial pressure. So now we have covered that. Let's see what Dalton said about partial pressure. Okay, so Dalton's law talks about calculation of total pressure inside this container. So we have already seen the calculation of partial pressures. Now Dalton said that if a container consists of non-reacting mixture of different gases, okay, so non-reacting is important, that is, say the three gases again from the previous slide are present in a single container. So these three gases have to be non-reacting in order for us to apply Dalton's law over there. They cannot react with one another under those conditions of temperature and pressure. So in a mixture of non-reacting ideal gases present inside a container, the total pressure exerted, okay, or the total pressure experienced inside this container is simply going to be algebraic sum of individual partial pressures. Alright, so total pressure is sum of partial pressures of all the gases inside our container. Let's say total pressure is represented by capital P or P with subscript T. So total pressure, okay, is simply equal to partial pressure of gas 1 plus partial pressure of gas 2 plus partial pressure of gas 3. Okay, and this is a very important law. Alright, so you will very often use this formulation of Dalton's law even in your class 12th. Okay, so and it's pretty simple also, right? It's just like when you add mass, total mass is equal to sum of individual masses. Similarly here Dalton said for ideal gas, and this is valid only for ideal gas, that total pressure is simply sum of individual pressures. Okay, you just make an algebraic sum and you will get the total pressure or total force per unit area. So here the word non-reacting, that the gases, in this instance the three gases present must be non-reactive in nature. Okay, because if they react with each other, then their amounts can change, right? We have studied stoichiometry in mole concept. So 2 moles of gas 1 can react with 1 mole of gas 2 to form say 10 moles of gas 3, right? That is a possibility, a theoretical possibility. So if amount changes, pressure also changes, right? Even though R, T and V is same for the same given container. That is why the gases must be non-reactive in nature. What happens if gases are reactive? Let's say you have hydrogen and oxygen inside a container and nitrogen, and under those conditions of temperature and pressure, hydrogen and oxygen are going to react with each other. Okay, so how do I make use of Dalton's law, or how do I calculate total pressure under such conditions? So what you do is you simply, okay, since nitrogen is non-reactive, we can simply use its number of moles directly, say N1. And for hydrogen and oxygen, you first react them. Okay, you react hydrogen with oxygen, and as a result of their reaction, let's assume under those conditions they form water vapor, okay, or gaseous water. So now you have made the reaction and the result is water vapor, and hydrogen and oxygen are no more present. Okay, let's say that they are completely reacting. So now you have nitrogen and oxygen, that is now you have two non-reacting gases. So you calculate moles of nitrogen and you calculate moles of hydrogen, water vapor. You calculate their individual partial pressures and then you add those individual partial pressures, okay, to get your total pressure as per Dalton's law. Alright, though in your syllabus, especially in your school, from your school level, you will never actually get a mixture where gases are reacting with each other. Okay, the questions which will be covered in your examinations will always have non-reactive gases, but still you must know this concept and how do we deal with reacting gaseous mixtures. Okay, so you simply react them and make sure that the products are not reacting anymore, and then you make the calculation. Okay, so that's it actually. Alright, so this finishes of Dalton's law, but we can further use Dalton's law to derive upon some more important formula. Okay, and a very important formula, a relation between mole fraction and partial pressure. Okay, see here, we know that total pressure PT can be written as for the same container. Alright, say this is my container having three gases N1, N2 and 3 in these quantities. Alright, temperature is T and volume of container is V. So the total pressure inside the container can be said to be, using ideal gas law, is NT RT by V, where NT represents total number of moles of ideal gas inside this container. Right, this is always valid. Ideal gas equation is always valid over here. So this formula is correct. Also I know that, okay, also I know that total pressure as per Dalton's law is simply sum of individual pressures. Okay, and what is the value of individual pressures? Say P1. So partial pressure of gas 1 is simply N1 RT by V. Similarly, partial pressure of gas 2 and gas 3 are N2 and N3 RT by V respectively. So just substituting those values here, I get NT RT by V is equal to N1 RT by V plus N2 RT by V plus N3 RT by V, or NT is equal to N1 plus N2 plus N3. Okay, that is, you cancel RT by V from both sides. This is quite obvious. Okay, this is quite obvious that if you have to calculate total number of moles, then you simply sum the individual moles of various gases, and that is another reason why gases have to be non-reactive in nature. Okay, unless they are non-reactive, this equation will not hold. Okay, if gas 1 and 2 reacts with each other, then they will just react and form some other gas in a very different quantity. Okay, so in order for this algebraic sum of number of moles to be valid, the gases have to be non-reactive. Okay, so this is how Dalton, you can say Dalton's law can also be derived. You start with this, that total moles is equal to N1 plus N2 plus N3. You multiply both sides with RT by V, so you will get this equation. Okay, and then you simply use the formulas of partial pressure and total pressure to convert this equation to this equation. Okay, and this you can say is the derivation of Dalton's law. Okay, this is just one way of looking at it. Though you have to remember Dalton's law, and using this we saw that total number of moles is equal to sum of individual moles. Okay. So coming back to the initial relation that I was talking about over here between partial pressure and mole fraction. So again, PT is equal to NT RT by V. Alright, and say you are talking about partial pressure of gas 1. So P1 is N1 RT by V. Let's say this is your equation 1, this is your equation 2. And what if now I divide equation 1 and equation 2? Okay, so what I get is, or instead of doing that, okay, let's divide equation 2 with equation 1. So if I do that, what I get is P1 by total pressure, partial pressure of gas 1 by total pressure, is equal to N1 RT by V, and in the denominator we have NT RT by V. This is N1 by NT, or you get P1 by PT is equal to N1 divided by NT, and we just saw what is NT. It is N1 plus N2 plus N3, right? So from here I get P1 by PT is equal to X1, where X1 represents mole fraction of gas 1. Okay, if you remember mole fraction, which we studied in mole concept, mole fraction is the ratio of moles of one component to total number of moles inside your container or solution. Okay, so here total number of moles is the sum of 3 individual moles, and N1 is the moles of gas 1 only. So N1 by N1 plus N2 plus N3 is the mole fraction of gas 1. Okay, so ratio of partial pressure and total pressure is equal to mole fraction. This is a very important relation. Okay, that P1 is equal to X1 into PT. Similarly, partial pressure of gas 2 will be equal to mole fraction of gas 2 into total pressure, and partial pressure of gas 3 is equal to mole fraction of gas 3 into total pressure. Okay, so in general we can say, or we have found another way of calculation of partial pressure. One way that we studied in the first slide, P1 is equal to N1 RT by V, that is using equation of state. The other way of calculation of partial pressure for any given gas is using mole fraction. Okay, so partial pressure is always equal to mole fraction of that particular gas into total pressure inside the container. Okay, this relation is again very important. Okay, we will use we can use this in thermodynamics, in chemical equilibrium, okay, in numerical questions of chemical equilibrium, and also in various chapters of class 12, especially in solutions chapter. This relation will come time and again. So partial pressure is equal to mole fraction into total pressure. Alright, or you can say ratio of pressures, that is individual pressure to total pressure, is equal to ratio of moles, that is individual moles to total moles. So a very important corollary. Lastly, let's analyze Dalton's law. Let's see why total pressure is simply algebraic sum of individual pressures. Okay, why is it not product or division or some other complex relation? So see, here we are talking about only ideal gases. Okay, and we have some very important assumptions in ideal gas, which we'll actually study in great detail in our next session. But one of those assumptions that we already know is that the forces of attraction between molecules of ideal gas are taken to be negligible or zero. Okay, hence if the gases are non-attractive, that is they are not attracted or they are not interacting with each other in any way, because we are also assuming non-reactive gases, that is they are not reactive and there is no attraction between the molecules, then you can say one gas is completely indifferent to the presence of other gas, is completely indifferent to the presence of a third gas, is completely indifferent to the presence of another gas present over there. Okay, so all these different gases, gas 1, 2, 3 and 4, there are 4 gases in this container, and all of them are indifferent to each other, that is all of them are behaving as if the other doesn't exist at all. And if that is true, then we can simply say that the individual pressures are not affected by the presence of other gases, and hence total pressure is simply going to be algebraic sum of the individual pressures. Okay, there is no complex relations over there, right? In fact, from here we can also understand that, say if initially you had only gas 1 and 2 inside your container, okay, there is no gas 3. Okay, so individual pressures are P1 and P2 and total pressure is P1 plus P2. What happens if I add another third gas in this container later on? How will that affect P1 and P2? So the answer is, the presence of third gas or the pumping in of a third gas even at a later time will not affect the value of P1 and P2. Why? Because P1 is simply N1 RT by V. Okay, that is R is same, T is same, V is still the volume of the complete container. So and N1 is still same, the amount of gas 1 has not changed, right? Only the amount of gas 3 has changed, but amount of gas 1 and 2 is same, hence their partial pressures will be same. Okay, only difference will be now total pressure, which was initially sum of P1 and P2 only, will also have a third component P3, but the values of P1 and P2 will be same as they were before the presence of gas 3. Okay, so that is one thing. Another thing we saw in ideal gas equation, PV is equal to nRT. Okay, that this equation of state tells us that there is a relationship between thermodynamic variables PV and T and the amount of gas. There is no relation between the type of gas and thermodynamic variables for ideal gases. So it doesn't matter whether I have moles of oxygen or moles of nitrogen. Okay, only thing that is important is the amounts of the gases. Hence I can treat moles of oxygen as same as the moles of nitrogen, right? Instead of talking about 2 moles of nitrogen, I can simply say I have 2 moles of oxygen and calculate the value of pressure. And if instead of say 2 moles of oxygen you have now in another container 2 moles of carbon dioxide, then even then it will have the same value of pressure. Okay, so hence the total pressure or even the partial pressures are dependent on only moles and not the type of gas. Okay, from both due to both the reasons. One is the qualitative reason, that the force of attractions are not there. The other is simply from mathematical point of view, that the equation of state doesn't differentiate between type of gases. Okay, and hence Dalton's law is applicable or can be seen or understood, okay, up to some level using these this theory or these concepts that we just saw. So in the next session we will talk about kinetic theory of gas, and that will wrap up our ideal gas equation completely. So until next time, and once again thanks for watching Edupedia World videos.